If I stand on this skateboard,
I started out wanting to be a paleontologist, then I thought maybe computers. By the time I got to college, I decided on engineering physics, which some people see as a cruel joke, but for me it was like I'm keeping my options open. I could work in any lab if I do physics. My freshman year in college, my first year physics class, our professor, Corbin Kovault, had the occasional demo in class. The one that really stuck out to me was he took out a cinder block, placed it on his hand, and just started smashing it with the hammer. He also ate a piece of chalk once, so fun guy. My name is Zach Tobin. I'm the physics lecture hall manager here at Caltech. There is a very strong history of physics demonstrations here at Caltech. Especially this last year, one of our main thrusts with these demos is digitizing them and having this archive online with information on the demos and the videos. I think I've recorded about 180 demos. Probably number one for me is what I call the Cannihilator now. We charge a huge capacitor. It weighs like 100 pounds just by itself, up to a few kilovolts, and we discharge it through just this small coil with a soda can in the middle. The electromagnetic forces induce a current in the soda can, and they all interact and they just rip the soda can apart. There's another really simple one, you can even do it at home, where you take a battery, like a AA battery, you hang a screw off of it, and then you just wrap a piece of wire around. You can hold it all up with your hand, and the screw will start spinning because of the electromagnetic forces in it. Very simple, very fun. I like seeing everyday objects behave in ways you don't expect them to behave.
They think that they're so fancy with their literature and art. But we've got Klingon, Hamlet, which our younglings learn by heart.
I've been involved in theater with Caltech since I was a grad student here. I built Klingon weapons for our Star Trek production, Boldly Go. My favorite production that we did here was Little Shop of Horrors, where I got to help build and puppet the plant Audrey 2. What I hope people walk away from our videos seeing and thinking is, that was interesting, physics is interesting, I want to learn more. Hello, I am Zach Tobin, and I manage the Feynman Lecture Hall here at Caltech. I should say I am not just a physics lecture hall manager, I am the physics lecture hall manager. If you Google the phrase physics lecture hall manager, all that will come up are pages about me and my predecessors here at Caltech. So yeah, it's a pretty unique job, but that's not to say I'm the only one that does it, just that it's so unique that there's not really a standardized title for it. You might see others called laboratory equipment technicians, demo managers, or lab coordinators. The general name we refer to ourselves as is physics technicians. Now, what most of you might eventually come to know us from is our demos. You see, every year, all of our freshman and sophomore physics classes are held here in the Feynman Lecture Hall. And every week, I set up about a dozen or so physics demonstrations for those classes. So I assemble them, put them up, tell the professors how to use them, and then it's also my job to fix and maintain them over the course of the year, as well as come up with new ones, design and build those too. So it's my job to play with toys. Now this is going to be a little bit different from the regular science journeys, in part because I don't technically do research, but also because we're on location at the Feynman Lecture Hall. And in fact, all those demos are stored just behind this door. So we'll take a little photo journey through that. So on the first floor is where all the stuff that gets regular use, including tools and common items, are stored. The second floor is where most of the actual demos are stored. And the third floor is deep storage, including some of our historical documents, but it also includes this little crawl space where I can lower things in from the ceiling. For example, our swinging bowling ball demo. Here, let me show you where I just was. Hey down there. Now, even in the land of minutia, that is academia, it's a pretty esoteric job here. So I have been asked on occasion, what led me to here? It all started when I was but a small human child. I knew I wanted to do something techie. First, paleontology was my interest. Then I was like, maybe computers. Eventually, I decided I wanted to do lab work when I grew up. But when it came to college, I wasn't sure what kind of lab work. Electrical engineering, mechanical engineering, chemical engineering. I mean, there's material science, civil. It all sounded so interesting. I couldn't make up my mind, so I went with engineering physics, because physics is like the basis for all engineering, kind of. I know engineering physics is going to sound like a cruel joke to some of you, but to me it sounded like I'm keeping my options open and learning about everything. Eventually, the next step is getting a PhD. So this led to me working in the plasma physics lab with Professor Paul Bellin. I worked there for a few years. I built a plasma gun. I learned how to work in a lab. And I eventually realized that's not really what I wanted to do. I liked building and operating the equipment, but when it came time to do the actual science work, I found it wasn't super interesting to me what the cyclotron orbit of the electrons was as a function of how hot the temperature of the plasma was. I wasn't meant to be a scientist. And as it turns out, I wasn't alone in that kind of realization. About half of all PhD students don't actually graduate with a PhD. And that's how I came to learn the difference between a scientist and an engineer. You see, a scientist is all about curiosity. They want to search for answers. An engineer is all about solving problems. See, scientists, they research and they experiment. Engineers design and build. They use scientific principles learned by the scientists, and experimental scientists will use equipment built by the engineers. But in this little dichotomy, there's actually one slot missing: the technician. They solve problems like engineers, but they generally work with the equipment that's already there, or they take engineers' designs and work with them. All three of these jobs require a fairly hefty amount of skill, but where those skills lie tends to vary. Scientists, for example, tend to use the most math, while technicians use the least. Meanwhile, scientists tend to be the least hands-on with their skills. They don't use tools as much. They don't operate equipment as much as technicians do. And engineers are somewhere in the middle. Now, of course, these are wild generalizations. Plenty of technicians have higher level math education. Plenty of scientists know perfectly well how to use all the equipment and how to even build and design it themselves. Of course, not all scientists use as much math as others. A physicist is going to use more math than a biologist. But either one is going to use high abstract principles in their work, much more than you would expect them to use power tools. Meanwhile, technicians don't necessarily need to know about the anatomy of a cell or the wave function of a certain electron as much as they'll need to know how to use those power tools. So I enjoyed the engineering and technician aspects of the job, and as it turned out, I also liked theater, presentation, to a certain extent teaching, and that led me to the Pasadena Educational Foundation and the App Academy. The PEF is a nonprofit in Pasadena that functions to support the local school district. And I came in to help develop a program for a 4-year computer science course, the App Academy. In particular, I ended up helping develop and teach Android app development and robotics. But ultimately, teaching at a public high school was a little too stressful for me. And it was about that time that I stumbled across a job listing here at Caltech. They wanted someone with a fair amount of lab experience, someone who's been involved in education, someone who knows physics, preferably someone who knows a little bit about programming and web development. And as it turned out, all those disparate things I'd spent my life doing kind of combined into being exactly what I needed to know to do this job. Okay, so let's bring this back to why we're here. Why do we want to do demos? Why do we take time out of a busy lecture to just show you again exactly what we were just talking about, only even slower? As it turns out, demos actually serve a fair number of purposes. The most obvious one is engagement. People like looking at demos. It keeps them interested in what might otherwise be a dry, boring lecture. For example, here's a video of the whoosh bottle rocket. In it, I pour some methanol into a water jug, light it on fire, and it rockets across the room. That's Newton's third law. For every action, there is an equal and opposite reaction. In this case, the action is the flaming gas of methanol being ejected out one side of the jug. The reaction is the jug being pushed in the opposite direction. This is how rockets work. It doesn't really matter how old you are. A flaming bottle rocket being shot across a classroom is going to draw your attention one way or another. And from my experience in education, I can say the number one most important thing for learning is motivation. If someone wants to learn, they're going to learn. If they don't want to learn, it's a lot harder. And the demos, to a certain extent, get people interested in physics. In addition, with long, boring lectures, it can help to kind of give your brain a break for a second, watch something fun. See, to a certain extent, the presentation of demos also helps those of us interested in the physics and the technical aspects of it convey that enthusiasm to our captive audience. Now, we do these demos in a classroom setting, so the most important thing we want to consider is, do they help us learn? Well, the most important factor for whether a demo enhances learning of a certain scientific concept is if we can get these students to try and guess ahead of time what's going to happen at the end of this demo, and then show the demo and see if what they said or predicted actually happens. Hypothesis and testing, it's the core of scientific experimentation. Here, let's take a look at this one. I have here two bouncy balls, one big, one small. See if I drop them from about the same height, they bounce to about the same height, which is a little bit lower than where I dropped them from because they lose a little bit of energy on each bounce. So the question is, if I stack them on top of each other, what's going to happen when I drop them? Right? Your first inclination will probably be they'll drop and then bounce back up to about the same height they would have if they weren't stacked. See what happens. The little ball bounced a lot higher than where I dropped it from. Why'd that happen? Well, you see, physically what happens is when I drop them, they collide as if I hadn't dropped them together. See, when this little one drops and hits the desk, it just hits a stationary desk. If I drop them together, it's sort of like what happens is this one hits the bottom and bounces up first, then this hits the big one. So instead of hitting a stationary desk, it hits something that's already going up. So it gets that little extra kick because this is already going upward. Physics. Another use for demos is clarity, making sense of complicated concepts. You see, a lot of science, and especially physics, can look like just a bunch of random letters and numbers on a chalkboard. But with good demos, you can kind of make an intuitive sense out of what we're seeing. Here. Here we have Faraday's law and Ampere's law in differential form, and Ohm's law. Now what they say is if you have a changing magnetic field, it will create a voltage. What this says, once we just kind of ignore this part, is if you have a current moving electricity, it will create a magnetic field. And what this says is if you have voltage, it will create flowing electricity, current, provided the resistance is low enough, like, say, in conducting metals. So if we combine all of these and say we drop a magnet next to some metal, well, the magnetic field by that metal is going to change. It's going to induce a voltage. That voltage is going to create a current. That current is going to create a magnetic field. And what this negative sign tells us is that that changing magnetic field is going to oppose the moving magnet. That's really dense, isn't it? Fortunately, we have a demo that might make this a little bit easier to understand. Here, I have a copper tube and a strong neodymium magnet. I'm going to drop this magnet in the tube. Sure took it a while, right? You see, the moving magnet creates a current in the tube, which creates a magnetic field that opposes the magnet. And now we can see what that really means. If you move a magnet by a piece of metal, the metal is going to try and stop that magnet using its own magnetic field. That's Lenz's law. And of course, we can take demos and use them to learn history. See, science isn't just a bunch of facts. Science is a technique, it's a story. Our scientific knowledge doesn't just pop into existence. Everything that we know because at some point someone figured it out. And a lot of times they do the experiments that we later adapt into demos, like this storm bell. You might recognize this device from the opening scene in Aladdin, combination hookah and coffee maker that also makes julienne fries. Kidding. This is Benjamin Franklin's storm bell. Ben Franklin was a scientist in the 1700s. And he also did a few other things, but his most important achievements were in science. Everyone's familiar with Ben Franklin flying a kite in a thunderstorm, but that's not his only ridiculously dangerous experiment with lightning. You see, Franklin put an antenna on his roof and hooked it up to a bell in his house. And right next to it was a brass ball on a string and another bell. Now, when lightning strikes, the air fills with electric charges until it can't take how much charge is in the air, and it all collapses in a lightning strike. At the beginning, when those charges are floating around in the air, the antenna can collect them and put them on that first bell. And just like with a magnet and a piece of iron, a metal ball gets attracted to an electrically charged bell. It runs into the bell and it picks up some of that charge. And again, just like with magnets, opposites attract but alike repel. So the positive bell repels the positive ball. The ball hits the other bell and deposits some of its charge on the bell. We can then hook up that bell so it just gets rid of that charge once it has it. So now the ball has no charge. The bell on that side has no charge, so the ball gets attracted to the first bell, hits it, gets some charge, gets repelled, hits the other bell, loses its charge, and so on and so forth. Since you have this brass ball hitting the bell before lightning strikes, it was basically a lightning alarm. So we call it Franklin's storm bell or Franklin's storm detector. The dude had just invented the lightning rod to keep lightning from hitting houses, and he up and uses it to pull the lightning right into his house. So here we have our lightning rod antenna. We got two bells and a little ball in between. And of course, we have our artificial lightning. And now we know a storm's coming. All right, I have one last demo for you, just for funsies. It's called Shoot the Monkey. This demo starts with a hunter. And he's got his gun. And he's hunting a monkey. Why is he hunting a monkey? He's some kind of jerk. A lot of physics problems are really violent for some reason. Anyways, we got the monkey over here in his tree. Monkey spots the hunter. Hunter spots the monkey. Hunter fires. But because the monkey's been keeping tabs on the hunter, monkey decides to drop right as he sees the hunter pull the trigger. So, by the time the bullet gets to the tree, the monkey's all the way down here. Thus is his plan to escape the bullet. Let's see how that goes when we actually try it out. Don't worry, we're not going to hunt an actual monkey. It's just a plushie. We're going to hang him up using this electromagnet that is triggered by this dart gun. See, I'm going to point it directly at him using this special laser sight, and when the trigger is pulled, the monkey will drop. Monkey still got hit. I'm afraid so. You see, once that bullet leaves the gun, it's in a ballistic trajectory. It's going to fall, just like this ball here. Except, a lot faster because it's a bullet. You see, once it's no longer under the effects of exploding out of the gun, it's only feeling gravity, the same as the monkey once it's released. So that trajectory that the bullet was fired in is actually going to look a little bit more like this. Its trajectory is going to drop by exactly the same amount that the monkey dropped, because they're under the exact same forces. See, this is going to happen even if this happened on a different planet. Say if he was hunting a space monkey on Rigel 3 and gravity was only half of Earth. The monkey gets half gravity, the bullet gets half gravity, everything falls the same amount. Thus, the monkey's clever plan is ultimately what dooms it. So with that, I hope I've conveyed a little bit of my enthusiasm for demonstration. If you're interested in seeing more of these demonstrations, you can check out physicsdemos.caltech.edu, where they are all archived online. And I hope you've learned that there's more to science than just research. There are teachers and professors, lab managers, technicians, engineers. STEM isn't a one-size-fits-all field, and it can sometimes be difficult to see that when you're on the inside of it. That's my time. Farewell.
Thank you for attending today's Science Journey presentation. Here at Caltech, we thank Mitch Aiken and Kitty Cahalan of the Center for Teaching, Learning, and Outreach, as well as Mary Herrera and Kara Steeman from the Office of Public Programming, and the teams from Academic Media Technologies and Event Productions. And special thanks to Robin Javier and Brian Brophy. Additionally, we thank the Caltech Employees Federal Credit Union, the Friends of Beckman Auditorium, and our many sponsors who make these programs possible. We look forward to you joining us again for future science lectures and performing arts events. Learn more by visiting events.caltech.edu.